people online cannot hear me, let me know. I'll try to speak up a little bit. Yeah, so this is going to be sort of a quantum computing talk, but not really. And my motivation for giving this talk is, of course, Yuri. That's also the reason why I'm here. Right? So Yuri has this amazingly wide sort of breadth palette of things that he worked on. He's worked on logic, of course, computability, complexity theory, algorithms, proofs, and also quantum computing, let's say somewhat more recently. And I never had any joint works with Yuri, unfortunately. That's not something I can talk about, but I'll try to sort of give a talk that combines the last two topics. So what I want to do in this talk is to sort of show you examples of how the mathematical tools of quantum computing can be used as a proof tool for other things. Right? So combining quantum and proofs, and we never have to worry about building the hardware, right? Because everything I'm going to say can be done on paper. And this fits within a much more general theme, and a general theme, which I think is one of the reasons people like mathematics. It is that proofs can come from all sorts of unexpected corners. And I think this is one of the beauties of our field, surprising proofs. And before going to the quantum, I want to give you some examples of somewhat surprising proofs. And all of these proofs have the same feature, namely that you prove something about X, and you import into your proof tools from area Y, which has nothing to do with X. Right? And here's a very simple example from high school, which is how to use complex numbers to prove things about real valued functions. Right? So for instance, this is an identity in trigonometrics. And I can never remember these things. For instance, why is there a minus sign instead of a plus sign? So you can ask yourself, okay, how can I derive these things? And of course, the easiest way to derive these things is to go from the real numbers to the complex numbers. Use Euler's identity, right? E to the ix equals cos x plus I times sine x. Let's try to prove the above identity using this Euler equation. Right? So the left-hand side, cos x plus y, is really the real part of e to the I x plus y with the x plus y in the exponent. And this you can nicely factor as a product of e to the ix times e to the iy. For each of those two factors, you can use the Euler identity. You can write it out a little bit. And you sort of see the i's and the I squares appearing. The I squared is what gives you the minus sign. And now you just sort of project away the imaginary part. You keep only the real part. And it is the right-hand side of the identity that I wanted to prove. Right? This is, of course, kind of trivial math. But it illustrates a general principle that I want to talk about here, which is we prove something about the real numbers, and we use stuff from the complex numbers to prove it, even though the statement we're proving has nothing to do with the complex numbers. Right, and let's say more involved example of the same general phenomenon is the probabilistic method. We saw some beautiful complicated examples in the previous talk. A probabilistic method is sort of the use of aspects or properties of probability theory to prove things that have nothing to do with probability, right? The existence of certain trees, for instance. And Manfred gave some complicated examples. I'll give you a very easy example so that we don't have to think about it. So here's a theorem about graphs. Every finite graph with, let's say, finite undirected graph with a vertex set V and an edge set E that has m edges, admits a cut with at least m over 2 edges. So what is a cut? It's just a bipartition of the vertex set into two parts, the set T and the set T complement. And an edge will be considered cut if it goes from T to T complement. Right? So you sort of throw away the edges that go from one part to its complement. So that's a cut. And if I claim that if you have m edges, then there will always be a cut that has that cuts at least m over 2 edges. And there's many ways to prove it. One nice way to prove it is using probability. This example, by the way, this cut would have size only 2. My theorem, because there's like, 6 edges, my theorem claims that there should be a cut with at least 3 edges. And I'm sure you can see it, right? You can, for instance, like put ABD on one side and CE on the other side, and this will cut at least 3 edges. So let's give a simple probability-based proof of this theorem, which has nothing to do with probability. So the first thing to do, and this is kind of often sort of the first move in a probabilistic proof, is you just choose your bipartition uniformly at random. So for every vertex, you decide whether to put it in T or in T complement, 50-50 probability. Very easy. And then let's define a random variable. For each edge ij in the edge set, I'm defining an indicator random variable xij, which I set to 1 if that edge happens to be cut by my choice of T. and I'm setting this indicated random variable to 0 otherwise, right? It's just a truth value of the statement edge ij is being cut by my choice of t or not. And now you can look at the expected value of xij. Yeah, xij is just 0 or 1. So the expected value is just the probability that the edge is cut. And if you pick your bipartition at random, then it's easy to see that this probability is a half. Right? With probability 1/2, I and j will land on different sides of the bipartition. This is 1/2. But now you can actually look at the expectation of the total number of cut edges, because the total number of cut edges is just the sum of all these xij indicated random variables, summed over all the edges of the graph. You can use linearity of expectation to sort of just isolate the ij terms, whose expectation we have already calculated. So that's m over 2. Right? And now how do we conclude the proof? So the left-hand side of what I just derived is sort of the average over all cut sizes if I pick my bipartition uniformly at random. This average is exactly equal to m over 2. But that can only be if at least one of the things in this average have cut size at least m over 2, right? Because I'm averaging non-negative numbers here. So then the punchline is there must exist a t with at least m over 2 cut edges. Right? And this is really one of the simplest examples of the probabilistic method. I'm just illustrating the principle here. And the principle is you use tools from an area, namely probability theory, that has nothing to do with the area where the theorem that you're proving lives in, which in this case is graph theory. Right? And there's beautiful examples. There's whole books written about this. They're full of beautiful, very surprising examples, often in things like discrete math and combinatorics, but also in number theory and analysis and other areas. And an important example of the probabilistic method is to use information theory. So let me give an example of that as well. So here's an example of the use of information theory to prove a tail bound for the binomial distribution. So let's say that we flip n fair coins. Like each coin comes up 0 with probability half, comes up 1 with probability half. And you can, let's say, in this picture here, you see how this probability distribution looks like, I guess, for n equals, what is it, 70 or so, right? And this is, of course, a discrete approximation of the bell curve. And let's try to upper bound, or let's try to estimate the sum of the first d binomial coefficients. So n choose 0 plus n choose 1 plus n choose 2, etc. And what is the motivation here? Well, the size of that sum is essentially the left tail of this distribution. So this allows you to prove things like Chernoff bounds, like upper bounds on the tails of binomial distributions. So this is a combinatorial question, right? It's like, what is the sum? What is a good upper bound for the sum of these binomial coefficients? And my claim is, this is well known, it's at most 2 to the power n times the binary entropy of the number d over n. Right, so d over n is some number, at most a half. There's going to be a binary entropy of this. The binary entropy is this function here. And you should think of this as sort of measuring how much information there is in a random bit. If your random bit is like 50-50, the information in that random bit is a half. You learn 1 bit of information, is 1. You learn 1 bit of information if you get the outcome of the coin flip. And otherwise, it's a little bit below. Right? So for instance, if d over n would be like 10%, then the entropy of d over n would be somewhat like 0.3-ish. The main point here is that the upper bound will be sum of binomials. In the exponent, it has a constant that's going to be strictly less than 1, unless you go all the way to the middle of the distribution. And let's try to prove this with information theory. And it's really very simple. And it's also totally different from the usual proof of a Chernoff bound. So I'm first going to define the set of all binary strings of length n, whose Hamming weight, number of ones, is at most the number d. What is the size of that set? That's exactly the sum of binomials that I'm trying to estimate. Right, so what I want to do is I want to upper bound the size of the set S, because that's exactly what the sum of the binomial coefficient. And what I'm going to do, I'm now going to do a little bit of information theory. I'm going to pick an element, an n-bit string, from the set S uniformly at random. Right, so I'm thinking of this as a random variable. And you can think of that random variable as actually the concatenation of n binary random variables. And what is the probability if I do this, if I pick this capital X, what is the probability that a particular bit, let's say the ith bit, that this is equal to 1, that probability is at most d over n, right? Because all the strings in my set, Hamming weight at most d over n, it's kind of uniform. So if I pick pick a string from this set and I look at a particular position I, the probability that there's a 1 there is really at most d over n. And that means that the entropy of that individual bit xi is at most the entropy of the number d over n. I think 10% or something. Okay, so here comes the punchline. So if I look at the logarithm, the binary logarithm of the size of s, this is actually the entropy of my random variable x. Because if you have a uniform distribution over a set, the entropy of that random variable is just the log of the size of the set. And notice that the thing on the left-hand side is really the log of the quantity I'm trying to upper bound. Now this x here, this is a concatenation of n separate but correlated random variables, x1, x2, up to xn. And now I can use something which is easy to prove in information theory. It's called subadditivity of information. So the entropy of the whole string is at most the sum of the entropies of the individual bits. And each of those I have already upper bounded. Right, and now you exponentiate left and right, and you get the claim that I made. And this claim is super tight. Like this is basically the best Chernow bound you can prove, maybe up to polynomial factors in n. Right, so yet another example of the use of an unexpected proof tool, in this case information theory, to prove something, to prove a statement, a combinatorial statement that seems to have nothing to do with probability, with information, etc. And there is also a Kolmogorov complexity-based version of this information theory method. And this is something that Alexander Shen referred to yesterday, and it goes under the name of the incompressibility method. Right, so these are just 3 examples of sort of surprising ingredients in proofs that you might not expect because the ingredients seem to have nothing to do with the statement that you're proving. And now you can sort of argue, well, that's really just a counting argument, right? You're doing a counting argument in disguise. And that's completely true. I'm doing a counting argument in disguise. But that's really beside the point, because if you use tools from a certain area, you also import the intuitions from that area. And those intuitions would not be available if you're just thinking about this as a counting problem. Right, so the languages of probability theory, the languages of information theory, the languages of incompressibility and Kolmogorov complexity, they give us intuitions and tools that would not be readily available if you just think of this as sort of a blank, like a plain counting problem. Right, so I'm thinking of things like large deviation inequalities, the Lova's local lemma from probability theory, chain rules of information, subadditivity, all sorts of stuff about Kolmogorov complexity. The good thing about the incompressibility method is you can import all sorts of algorithmic intuitions that you would not have readily available otherwise. Right, so you could do those proofs just in terms of counting, but you probably wouldn't find them because like the tools that you would need to write them down cleanly are not available if you just think of this as a plain counting problem. Right, so it's good to have these probabilistic techniques in your toolbox, and I'm sure Manfred would agree because he's just showed us that he uses it. What should I do?
Just check the...
Okay, please go ahead.
Photos that they're saying they cannot hardly hear the speaker.
Sure.
Can you speak up a little bit? I mean, or like hold the tools. It's a little bit awkward, but...
I can put it closer to my mouth.
Yeah.
Good. I'll also try to speak a little bit louder.
Yeah.
Okay.
Check. Can anyone in the chat tell us if they can hear?
1, 2, 3. Is it better? I'm both raising my voice and having the microphone closer. Okay. Please show me how to do it because I don't see how to get to the... Oh, there it is, yeah.
Oh.
Okay, I can try to speak even louder, but I don't know if that's really the problem.
Yeah, maybe just hold it like this and try, see if they can hear like that.
Can you hear like this? If I like really shout into the microphone?
Yes, that's good.
Okay, thanks. Okay, it's a little bit awkward, but I'll try that. Okay, so this is all just about the sort of the well-known probabilistic method, which has existed probably for a century or so, right? It's really counting arguments, but done in a way that gives you access to different intuitions. And with those examples sort of under our belt, I now want to move to quantum. which I want to claim is also one of these unexpected proof tools. Right, and now we know quantum information and quantum computing for things like algorithms and cryptography and breaking RSA and communication things, non-locality, which was also part of one of the talks yesterday by André. And for this talk, we're going to use quantum techniques as a proof tool for things that have nothing to do with quantum, so statements from classical computer science and classical mathematics. And why? For the sort of the same reason as before, quantum information and quantum computation is a very rich melting pot of many different branches of mathematics. I think it combines many more branches of mathematics than other sub areas. In particular, linear algebra, probability theory, group theory, geometry, combinatorics, analysis, other things. And the bonus, of course, of this approach is that this is a sort of an application of quantum computing that does not require you to build any hardware. Right? You can do the probabilistic method even if you don't believe in probability, if you believe in a deterministic universe. Similarly, you can use quantum computing tools as a proof tool for your mathematics with pen and paper, even if you don't believe in quantum mechanics or if you don't believe that a quantum computer will ever be built. It doesn't matter. And this is very good because building a quantum computer is extremely hard. Like billions of dollars are going into this and the progress is very, very slow. It's there, but it's very, very slow. And I'm going to give 3 examples if I have time. You have to stop me if I'm almost out of time. Okay. So first I'm going to show a lower bound on so-called locally decodable error correcting code. So this is a particular type of classical error correcting codes. They have nothing to do with quantum. And you can prove a lower bound on them using the tools of quantum sort of under the hood. Similarly, I want to prove lower bounds for linear programs. And lastly, I want to sort of construct low-degree polynomials from quantum algorithms. And these are all examples from my own research. And I'm talking about those not because those are the only ones, but because those are the only ones that I can competently talk about. But there are other examples where people have used quantum computing in all sorts of ways to prove things that have nothing to do with quantum computing. Okay, so before going there, let me just sort of get out of the way a similar counter-argument that people could have as they had against a probabilistic method. Namely, you could say that this is just linear algebra. So quantum states are vectors and quantum operations are matrices. If you have one quantum bit, it's described by a vector of 2 complex numbers called amplitudes. If you have a system of 2 quantum bits, it's a vector of 4 amplitudes. If you have a state of 3 qubits, it's a vector of 8 amplitudes, etc. So states are just vectors of complex numbers, normalized in L2 norm. And quantum operations, in a very natural sense, correspond to matrices. They're linear operations. Right? So that means that when we do quantum computing, at least on pen and paper, that's really just doing linear algebra. It's just a bunch of matrix vector computations. And that means that these quantum arguments that I'm going to give are really just linear algebra in disguise. And this is indeed true, in the same way that probabilistic method proofs are really just counting in disguise. And again, it's beside the point, because my counter argument is sort of the same. If you use the language of quantum information theory and quantum algorithms, you get access to intuitions and tools that would not be readily available if you just think of these things as linear algebra problems. Right? So you could do those proofs in the language of linear algebra, but you probably wouldn't find them. And even if you did find them, they're probably very cumbersome to write down. Because a lot of sort of theorems that you can use from quantum information are very nice shortcuts that strip away a lot of the linear algebra that otherwise you would have to write out explicitly, and that's a massive pain. Right, so conclusion is the same as for the probabilistic method. It's good to have these tools in your toolbox. Even if you don't care about quantum computing, it's good to have these tools in your toolbox. And not many people do, right? So you could actually get a competitive advantage in your field if you try to use these quantum computing tools in a completely unrelated field. Okay, so here's my first example. This is about error correcting codes. So who here is somewhat familiar with error correcting codes, or at least the basic idea of error correcting codes? Okay, not many. Okay, let me just give you the sort of the short summary. So the idea of an error correcting code is that you have a string of n bits that you somehow want to protect from errors. The way to do it is to write down the n bits in a longer code word of something like m bits by adding redundancy, sort of spreading the information over a longer number of bits by repetition, but also by fancier things. in such a way that if I give you a word W, an m-bit string, which is close but not equal to an actual code word of an encoding of X, you can actually decode the original X perfectly. So the fact that there's errors in this code word do not prevent you from recovering the X. And this is like error correcting codes are really a success story of computer science, both in theory and in practice. They're a very useful tool in complexity theory, and they're also super useful for all sorts of practical communications. Almost everything about error correcting codes is good. Like people have optimized this all over the place. So you have like linear time encoding algorithms, linear time decoding algorithms. The word length M does not have to be much longer than N, so you don't lose too much in terms of memory. They have one big disadvantage though, which is that if you really don't care about the whole X, but just about one or a few of its bits, you're still forced to decode the whole of X. And this is very inefficient, right? So suppose you use some fancy error correcting code to store, let's say, a whole book. So you write down a code word for, let's say, Hamlet or something like that, but you really only care about decoding the first sentence or maybe the first sentence of chapter 5. Typical error correcting codes, they force you to unpack the whole thing, to decode the whole book. And that's very inefficient if you really want partial information. So there is a notion of version of error correcting codes that solves this, and these are called locally decodable. So here what you want is, so this is something that's on top of the usual error correcting codes, an extra property. So we say that an error correcting code is Q-query locally decodable if there is a decoding algorithm D, which not only gets the corrupted code words as input, but also gets an index I. It has to recover the ith bit of X, and it can only look at a small part of this word W. So think of Q as very small, like order 1 bits or order log n bits. And the decoder is allowed to be randomized, and it's allowed to make a little bit of error, like a small error probability. And it's a little bit surprising, but these things actually exist, but they typically have a bad code length. So the hard question in these codes, sorry, this case should be a Q, is the optimal trade-off between the number of queries that you make, which is kind of the sort of a measure of the efficiency of the decoding, and the code length M. Like ideally you want both of these numbers to be small, but there is actually a trade-off between them, and we don't understand that trade-off very well. And because of the potential importance of locally decodable codes in practice, like it would be very nice to figure this out, and people have worked on this for 20 years with not too much success. And what I'm going to do is show you basically the only strong lower bound that we have for these things, which is a special case where you decode by only 2 queries. So you're only allowed, like when you want to recover X10, for instance, you're only allowed to look at 2 of the bits of the corrupted code word, probabilistically. So on some runs you can look at these 2 bits, on some runs you can look at those 2 bits, but per run you can only look at 2 of the bits. And I'm going to show that in this special case, the code length actually has to be exponential in the number of bits that you're encoding, which is terrible, but you know, it is what it is. The truth hurts, but not as much as riding a bike without a seat. And this is actually tight. There's something called the Hadamard code. That's a special kind of error correcting code. And it is 2 query locally decodable, and it has exponential code length. And the lower bound that I'm going to show you says that you can't improve on this. And this is still the only super polynomial lower bound we know for general locally decodable codes. And it was first proven using quantum, and I'm not aware of any proof without quantum. So I'm going to sketch that proof for you here on one slide. And just to remind you, we're proving something here about classical error correcting codes. The statement that I'm proving has nothing to do with quantum. But what I'm going to do is I'm going to take a code, right? So let's fix any locally decodable code C, which maps n bits to m bits, and which is actually 2 query locally decodable. And then I'm going to define quantum states that are associated with the different code words. So there's 2 to the n different code words. For every n bit string X, so I have a code word CX. And I'm defining a quantum state. Okay, I won't explain this notation, but what this thing is essentially is a superposition over the m dimensions of the code word with pluses and minuses in the amplitudes. So this is a way to define a quantum state. And you can think of this definition as mapping the n-bit strings to quantum states in m dimensions. And m dimensions is really log m quantum bits. And you should think of log m as relatively small. So this is kind of an encoding of a long classical string into a shorter quantum state. But let's see how short it can be. So using properties of the classical decoder, so this is where I'm shoving a lot of details under the rug, but by the assumption that there exists a classical two-query decoder, you can show that from this state phi x, which sort of implicitly contains the string x, you can actually recover, by appropriate measurement, individual bits of x. So this state phi x, you can think of it as a quantum state that has like n bits of information in it, which you can extract individually if you want by well-chosen measurements. And those measurements, they sort of come from mimicking the behavior of the classical two-query decoder. And these states phi x, they are m-dimensional. That means that the number of qubits needed to write them down is only like logarithmic in m. Remember, m is the code length we're trying to lower bound. So these states have log m qubits, but they actually predict each of the n bits of x with good probability. And now there's a lower bound that was proven by Ashwin Nayak, that such quantum states, if they have a certain number of qubits and they allow you to predict any one of n bits, they actually must have a length that's proportional to n. So the number of qubits in these things is some constant times n, right? But if you exponentiate left and right, you get exactly what I claimed. You get an exponential lower bound on this code length. And again, the conclusion of this theorem has nothing to do with quantum, but we sort of dive in this quantum pool, we work with it, we come out on the other end of the pool, we're on dry land again, we're not talking quantum anymore, and we've proven something that we didn't know before. Okay, let me see how much time I have. 18, 1-8. Oh, okay, that's great. Good. Okay, so this was my first example. So the second example is something that made a bit of a splash, but on the other hand, the quantum component in it is smaller. It's more, this is going to be a classical proof that was inspired, or that uses as an ingredient something that was earlier proven in quantum. So let me explain this example. So this is about solving the traveling salesman problem by means of linear programs, right? Traveling salesman problem, one of these famous NP-hard problems, probably takes exponential time to solve. Linear programs, on the other hand, by a famous result of Kacchian, are solvable in polynomial time. So what is the TSP? So you're given like a map with, let's say, n cities and a matrix of distances between pairs of cities, and you need to find the shortest route that goes through every city exactly once. So this picture here is an example of the shortest route that goes through all of the 48 capitals of the 48 lower US states, excluding Alaska and Hawaii because that's not contiguous. Right, so you're given such a map and you want to find the shortest route that goes through all of the n cities on your map. And you can sort of turn this into a geometrical problem by writing down, so a cycle that goes through all of the cities is called a Hamiltonian cycle. You can write this down as a binary string of length n choose 2, just by an indicator of the set of edges that's present in your tour. And you can actually take the convex hull of all of those Hamiltonian cycles, and this gives you a polytope. And it's a polytope in dimension n choose 2, because each Hamiltonian cycle is a subset of the n choose 2 possible edges. And what is TSP? It's just to minimize a linear function over this polytope. And which linear function is that? It's just the length of the Hamiltonian cycle. Right, so you can think of this now as a linear optimization problem. And this is kind of good. It's starting to look a little bit like a linear program. The question is, if you want to turn this minimization problem over a polytope into an actual LP, you're going to have to write down the linear constraints that are valid for this polytope. That's how you get a linear program from this. And the fewer inequalities you need, the smaller is your linear program and the faster you can solve it. Unfortunately, this polytope by itself, the one in dimension n choose 2, it's not too hard to show that it needs exponentially many inequalities. So you can write down a linear program for this, but it's going to be exponentially big, right? And now you can solve this exponentially big linear program in polynomial time. You have not made any progress. But there is a very nice idea called extended formulation, which is that you go to higher dimension and reduce the number of inequalities. So here's a very simple example. You can take this picture here in R2. And if you write this down, you need 8 inequalities to write this down. right? You can sort of see this. The red thing has sort of 8 facets. And it needs 8 facets. If you want to write this down in R2, you need to write down 8 linear inequalities. But what you can also do is you can go to a higher dimension, 3-dimension, and write down a 3-dimensional object, which is characterized by only 6 linear inequalities, and then project down by dropping one of its coordinates. And this is a method of writing down linear programs that in some cases can give you an exponential savings in the number of inequalities. In fact, if you generalize this red picture here from the regular 8-gon to the regular n-gon, then in 2 dimensions you need n inequalities, but in higher dimensions log n suffice. So you can sometimes get an exponential reduction in the number of inequalities by going to a slightly higher dimension. And there were people in the 80s who claimed that they could solve traveling salesman this way. So they claimed that they could write down this TSP polytope, which lives in dimension n choose 2. They could write it down as a projection of a much simpler polytope in slightly higher dimension. And a much simpler polytope, they claimed to write this down with only a polynomial number of inequalities. And if that is true, you actually prove that P is equal to NP, because you write down a small linear program that allows you to minimize over the TSP polytope, and that solves the traveling salesman problem in polynomial time. Right, so people didn't believe this. I mean, this was either like a big shock or just completely untrue. And it was kind of subtle. Like, I think this person had some credibility. He was a university professor. People pointed out bugs, and then he fixed those bugs, and then people pointed out new bugs, etc. And then Michalis Yannakakis, he set out to sort of disprove that any such method could ever work. And he almost got there. He proved that so-called symmetric extended formulations could not capture the TSP polytope. Like, every symmetric extended formulation for TSP needs to be exponentially big, right? But that leaves some sort of escape route for people like Swart, because they could just try to write down non-symmetric extended formulations and still claim that they solve TSP. And this was a big open problem for like 25 years to get an exponential lower bound on the size of all possible extended formulations, not just the symmetric ones. And we solved this in 2012. So we prove an exponential bound for every extended formulation of the TSP polytope. Okay, this is going to be a little bit technical. So Yannakakis already showed that what you need to do is you need to look at the slack matrix of the polytope, the original polytope, not the extended one. This is some huge matrix that sort of captures all the slacks of all the inequalities that are valid for all the vertices of the polytope. And you need to lower bound how many rectangles you need to cover the support of that matrix. Okay, if you know some combinatorics, maybe you understand what I mean. Otherwise, just sort of doze off for this slide. And what I did in a paper in 2000, this was a paper about quantum communication complexity, is I designed a big matrix for a totally different purpose, namely to separate 2 different kinds of communication complexity in a very strange model. I designed a matrix that had a very large rectangle covering bound. You could prove for that particular matrix a very large rectangle covering bound. And I always held this up as sort of my most useless paper ever, until it turned out, as my co-authors observed, that same matrix M actually also forms a submatrix of the slack matrix of the TSP polytope. Right, and I had already proven the required exponential rectangle covering bounds. Right, and I'm skipping a lot of details here, but the conclusion is that every extended formulation of the TSP polytope needs exponentially many constraints, exponentially many facets. Right, and this definitively kills off this Swart approach to trying to prove that P is equal to NP. And to be fair, you don't really need quantum for this proof. You just need this matrix. But the only reason we had this matrix is that it was useful in an earlier setting for quantum communication complexity. Right, so I'm taking a slightly pragmatic approach here. I'm also giving examples where you have like a classical proof that's kind of inspired by some quantum construction, and this is an example of that. And the third example I want to talk about very briefly is a connection between efficient quantum algorithms and low-degree polynomials. So there is something called the polynomial method to prove lower bounds in quantum computing. What it does is it shows that if you have an efficient quantum algorithm in a certain sense, it induces a low-degree polynomial. And usually the way the direction people use this statement is the contrapositive. They sort of, like, technically this is the statement, but it doesn't really matter. Typical application is the contrapositive of that statement. By proving lower bounds on the degree, you can prove lower bounds on the efficiency of your quantum algorithms. Right? So this is a way to sort of show limitations of quantum algorithms. And my PhD thesis was all about this stuff, but that's a long time ago. But you can also use it in the forward direction as a way of constructing nice polynomials. And those are a few examples I want to mention here. So you can use this method as a tool to construct low-degree polynomials with nice properties by designing efficient quantum algorithms. And let me just mention some examples. So suppose you have some Boolean function that maps the integers between 0 and n to the real numbers, and you want to give a very good low-degree polynomial approximation to this function. You can get it optimally from designing quantum algorithms. There's another thing called Jackson's theorem. Everybody probably knows Weierstrass's theorem, which says that if you have, let's say, a continuous function on a closed interval, you can approximate it arbitrarily well with a polynomial. Jackson's theorem gives you how low you can make the degree of that polynomial. It's kind of an optimal quantitative version of Jackson's theorem. You can reprove it using quantum algorithms. You can also look at rational functions, which are ratios of polynomials. There's something called Newman's theorem that says that if you allow rational approximations, you can get very precise low-degree approximations, for instance, of the step function. You can reprove it using quantum algorithms. Right, let me skip the details of this. Summary and outlook, we're supposed to have this nowadays. So I've talked about quantum proofs for classical theorems. In fact, this is the title of my talk. And currently, to be fair, this is really more like a bag of tricks than a fully developed quantum method. It's sort of a bunch of tricks that can be applied in certain contexts. There's some sort of classical proofs that are vaguely inspired by quantum, you know. Is this a quantum method? Not really. But you could say the same about the probabilistic method. It's also a bag of tricks. It's just a much bigger bag with many more tricks, but that's because it has been developed for many more decades than these quantum techniques. Interesting question is, where can we find more applications? Well, low-degree polynomials is an obvious one. If you need a low-degree polynomial for something, right, and you don't know how to do it, think of quantum algorithms. You might have to do a little bit of learning there, but it is a tool that probably your colleagues don't know. Encoding-based lower bounds. So this is closer to these random access codes and these locally decodable codes. Places where linear algebra and combinatorics meet. This is, I think, probably the best place where the quantum method can be deployed, because quantum computing is definitely linear algebra. And at the same time, it sort of has the discrete structure that you need in combinatorics. And there's a bunch of dots where I don't know what they are. I'm actually hoping, you know, that people can find applications in logic, in automata, etc. But that's not quite my expertise, unfortunately. Right, so short summary, take-home message. It's good to have quantum techniques in your toolbox, even if you don't believe in quantum. So that concludes my talk.